Hello, everyone. My name is Giacomo Beccari. I would like again to welcome all of you to the new event, the second to last, I must say, event, unfortunately, of the ESO Cosmic Duologues series. As usual, I would like to start by thanking the speaker of today and our colleague Paola for organizing the event and for joining. Make it possible. Thank you very much. The topic of today, dust hight Z, as you can see already from our advertisement. As I said, this is the second to last event. Let me just remind you very quickly, the event is gonna stay on YouTube, on this channel, so you can see the event again in the future. Please, during this event, you are super welcome, everyone, to participate to the dialogue through our live chat that is available on YouTube. You can type your question, you can type your comments, have a lively comment, a lively session. You can participate in a sense, even though virtually, to the dialogue by contributing to the live chat. Or if you do not have a Google account, you can also send your question or comment to our email address, isoduo2020@iso.org, or you can also go to our page, duo.iso.org. There is a form there that you can fill, and the question will be sent. And we are monitoring the question live, so any question will be answered. Hopefully, the most of them. Anyhow, what we're gonna do after and we have done this already for all the past events, we are gonna collect all the majority of the questions, and we will give them to our speaker, and then we collect all the contribution into a brochure that is made available then on our pages. So you can, in fact, if you go to the page duo.iso.org, you will see on the right hand side you have the duologues link to all where you can see all the previous duologues. You have also the links to the live streams event that are recorded on YouTube, but you also can download material. Among them, you can download the PDF or the questions and answer in the form of an interview, if you want, from the other speakers. So having said that, I want to thank again Henri Boffin, my colleague Henri Boffin, for the big help and contribution in this to make the event possible. And with this, I will stop and I will immediately give the stage to Paola for the starting of the meeting. Have fun, everyone, and see you.
So thank you, Giacomo. Hello, good morning, and good afternoon, and good evening, according to where you're sitting and from where you join us. My name is Paola Andreani. I will chair this event, this Cosmic Duologues, as Giacomo was introducing us. So we have chosen this topic, dust at high redshift. Why? Because, as you know, dust is a key player in a star formation process. And for our understanding, not only of a nearby star forming process, but mostly at high redshift and the very early universe, it's very important to understand and to infer the amount of dust in an early galaxy. So that's why we have invited two experts in this field. Maruja Bradac, she is a professor of physics at UC Davis in California. And before that, she has been an Hubble Fellow at UC Santa Barbara. And before that, a postdoctoral researcher in Stanford. And she got her PhD at the University of Bonn. She's an observer, so she makes extensive use of the Hubble Space Telescope and the Spitzer Space Telescope, and of course of ground-based instruments such as Keck on the Hawaii. Professor Andrea Ferrara is a theoretician, is a full professor in cosmology at the Scuola Normale in Pisa, and she also joined professor at the Institute of Physics in mathematics in Tokyo. He's a well-known expert in his field in the physics of the early galaxies and the black holes. He has received quite a number of prizes, and is also currently chairing the advisory board of the Square Kilometer Array. So congratulations to both, and thank you very much for joining us. Let me first quickly introduce the topics, and then I give the forum to the two speakers. So I just would like to introduce historically the question of dust. Optical astronomers already decades ago have realized that when looking at the stars, there were stars whose flux and brightness have been dimmed by a foreground material. And they have first started inferring what is now well known called the extinction curves, where representing the amount of light absorbed by the dust in front of the star. And as you see, the absorption is very important at very short wavelengths, particularly in the UV and in the optical. So only with the advent of their infrared satellites, so those are able to observe outside the atmosphere, where in particularly IRAS made a really breakthrough in the field, because observing the nearby skies made clear that there is a big part of energy emitted in the far infrared, which was completely missed and neglected in decades before. And that's, of course, after IRAS, a series of more advanced satellites have been flown, ESO, Spitzer, Herschel, just to name the most important ones. And of course, we are aiming at seeing more results from the next generation of one. Just finally, why this is a very hot topic nowadays, because when you look at the cosmic backgrounds in the optical and in the far infrared, you see in these plots that the amount of energy in these backgrounds are comparable. So this figure shows the amount of energy as a function of wavelengths, and it compares this with the cosmic microwave backgrounds that, as you know, has the largest energy content in the universe. But as you see, both in the far infrared and the optical, these two backgrounds have comparable energy. So we need to understand what are the sources of this far infrared background, because we see in the nearby universe only 30% of the sources emit in the far infrared. So very likely these are the sources at higher redshift responsible for the primeval formation of stars. So I stop here and I give the forum to Marusha. Please, Marusha, share your slides.
Thank you very much, Paola. So let me just share this screen. Okay, hopefully everybody can see this. So today I was asked to sort of give a little bit of an observational overview of what we know about dust, but I decided that rather to tell you what we know about it, which is very little at high redshift, to be honest, I'm going to give you a couple of puzzles of star formation at high redshift and how dust is involved in those puzzles. Hopefully this will spark some discussion, and in the spirit of a true duologue, we will be able to talk about this more and hopefully maybe even answer some of those puzzles today. So dust at high redshift is important because we want to learn about two things at high redshift. One is how did reionization happen, and the other one is how it's linked to star formation. So basically we're trying to answer a couple of very simple questions, which are: when did reionization happen? How did it happen? Who did it? So who were the sources? And how is star formation from the earliest galaxies linked to reionization? And why do we even care about reionization? Well, we care about reionization because it's the earliest, it's linked to the earliest star formation and the earliest galaxy formation that we know of. And so in order for us to answer how did first galaxies come about, those things are intimately linked to the reionization epoch. It's also one of the least explored epochs in the history of our universe. So that's why it's important for us to know more about it. So why even puzzles? The onset of star formation has long been thought to be around 400 million years after the Big Bang. This has slightly been shaken basically by some, I should say, mildly controversial results from the 21 centimeter detection, which was unusually deep and unusually strong signal, which has indicated that maybe there is something exotic going on. And one of the exotic answers was that that the low mass galaxies are very efficient in forming stars, and that they might be forming stars earlier than we initially thought. The problem with these results is that a lot of garbage, as we call it, ends up at 70 megahertz, which is where the signal was observed. And so it's not quite clear whether we are indeed seeing something, some signal from primordial galaxies, or are we actually seeing some dust from our own galaxy or something similar. So instead, we were looking at clues of where did star formation start, when did star formation start, rather than looking at in 21 centimeter, we started looking at with galaxies. So let me introduce to you the curious case of MAX 1149 ZD. That's the galaxy we detected for the first time in both channels with Spitzer, with the SURF-SUP survey, SURF-SUP standing for Spitzer Ultra Faint Survey Program, slightly contrived acronym, but made for a cute logo. And so this little red blob that you see in the center doesn't look like much to the eye, but it actually presented us with a great puzzle. So when you look at spectral energy distribution, which is plotted here, which is observed flux density on the y-axis as a function of observed wavelength in the left-hand panel, you notice that while this galaxy has a normal slope in the rest frame UV, the rest frame optical wavelengths, this is around 4,000 angstroms, are very red. So the Spitzer color is very red. And the question was, why is this Spitzer color very red? And it was with the work of Hashimoto et al., who measured spectroscopic redshift of this object using ALMA, that we managed to constrain the stellar population in this object. And this is plotted in the two lines. So the blue line is the contribution from young stars, and the black line is the contribution from old stars. Old in this case means about 300 million years. It turns out that 80% of this galaxy light is likely being contributed by these old stars of 300 million years. Now, you might say 300 million years is not that much, but the problem is at redshift 9, at which redshift this galaxy was observed, the universe is only 550 million years old. And as such, this galaxy therefore poses an onset of star formation of around 250 million years after the Big Bang. So that was sort of uncomfortably early. Of course, before jumping to the conclusion, you cannot just say that's early star formation, because there are a couple other solutions of why we can have such Spitzer color. One of them is, as I mentioned just now, significant contribution of the old stellar population, but it can also be strong emission lines, because if you go back, you can see that these emission lines that can contribute to Spitzer fluxes. So the strong emission lines we have in mind are O3 and O2 NH beta emission lines. Well, turns out that there is yet another possibility, and that's it's dust that is causing this strong optical rest frame optical red colors in this galaxy. So to look more closely to this possible solution, the strong emission lines are excluded from this answer, mainly because the redshift is very well determined for this source, and all the major lines that could possibly contribute significant amount of flux are redshifted out of Spitzer's channel 1 and channel 2 bands. So the nebular emission lines are out, and that would also make it a very young stellar population. But as I said, given the spectroscopic redshift, this is not a possibility. Another possibility, as I said, is dust. But even with dust, we have a little bit of a problem, which is that if you look back in the plot, you can see on the bottom right corner, which shows the dust continuum, that there is a non-detection in with ALMA in dust continuum. In addition, I forgot to mention, in the upper right panel, you have the O3 emission, and O3 emission also gives you some indication of how much young stellar population there is. And so there is also a limit to how many young stars you can have in this galaxy. And so here is where at most 20% of the flux can be contributed by the young stellar population comes from. So let me come back to the dust. So ALMA non-detection makes a presence of significant amount of dust, hot dust, unlikely. So that doesn't mean that there is no dust, because there are different ways of making dust. And for anybody who's ever looked under the bed, you will notice that dust has a great ability to hide. And so in a similar fashion, dust also has a great ability to hide from observation. So it's not necessarily true that there couldn't be no dust. It's just the kind of dust that ALMA would detect is not likely present. Another question that then we have is, how do you make dust in 500 million years? That's at 500 million years after the Big Bang, I should say, because that's a very short amount of time where you can make dust. And I'm sure Andrea is going to touch more about the problems of making dust at high redshift. So the solution to this problem of what is causing this red color is either we are having an early onset of star formation, much earlier than we originally thought, or we have undercover dust. And either of those are basically an extremely exciting possibilities, because either of those are challenging the paradigm of our galaxy formation. So one thing I need to add, I have a disclaimer here, it's a small sample statistics, right? We are using one object to say something about the universe as a whole, and that's an extremely dangerous thing to do. Some people say, well, it's a pink elephant, right? If you see a pink elephant, what do you conclude? That it's unlikely to have a pink elephant, or the universe has pink elephants? And so it might be that this galaxy is indeed telling us something about the general population, but it might also be a very weird case. So for that reason, my graduate student, Victoria Strayed, went on to hunt more of such galaxies, which we will detect with Spitzer. And this is one of such galaxies from her latest paper. Right now, she's actually speaking at the same time at a conference about this. So if you want to know more about these topics, you can go to the recordings of CESAREC conference after this. But what she has found in Spitzer data is many more of such objects that show high promise. And here is an example of her work on the focus on the right-hand side, where she's plotting the time since Big Bang, where the star formation started. And for this particular galaxy behind Able 1763, she found with high likelihood the stars to be starting forming earlier than 200 million years after the Big Bang. And so it's quite likely that this is another case of such a galaxy similar to MAX 1149. It's still lacking redshifts, spectroscopic redshifts, so we are working on this. But in any case, there looks to be at least some more cases where we'll be able to study this kind of early onset of star formation. So that was my first puzzle. Let me go on to my second puzzle, which comes from UV spectroscopy. So Spitzer has been great in measuring colors, and it has told us fantastic things about high redshift galaxies. But if a picture is worth 1,000 words, a spectrum is worth 10,000 pictures. And so a spectrum as such can tell us a lot more than just simple colors. And where we use spectroscopy to study reionization timeline is with Lyman alpha emitters. So here's a schematic of how we do this. So for example, if you have a sample of Lyman alpha emitters at redshift 6, and if there was no reionization or nothing changed whatsoever, at redshift 7, you would see the exactly same population as at redshift 6. But since we know reionization must have concluded sometime around this time, it can conclude either in a patchy way, in which at redshift 7, you would see a couple of galaxies absorbed and the other ones coming through. And so that's what we call number evolution with efficiency of 0.5. Or you can have what is simply called smooth reionization, and you can simply dim all those Lyman alpha emitters. So if you look at redshift 7, at the comparable samples of high redshift galaxies, their Lyman alpha emission is going to be a lot weaker. So you will see a lot weaker equivalent width at redshift 7 compared to redshift 6. So we use this technique to actually study the reionization timeline and infer what's the neutral fraction. So these two toy models that I presented here have a sort of neutral fraction of around 0.5. But of course, we don't want to simply do this with toy models. What Charlotte Mason has been doing is she's been modeling the observations of Lyman alpha emitters in a fully Bayesian way and ask herself what kind of reionization timeline and what kind of IgM neutral fraction plotted here on y-axis can explain the observations of Lyman alpha emitters. We have hundreds of Lyman alpha, Lyman break galaxies that we observed, and we are measuring equivalent widths of those, and we are looking at how the equivalent width of observed high redshift galaxies that are selected as Lyman break galaxies, how they change between redshift, say, 6 and 7. And so these are the stars. And what happens when you use Lyman alpha emitters to tell you about reionization is that they prefer early reionization. So these pink lines or purple lines basically fit Lyman alpha emitters. And whereas if you just use CMB and Lyman alpha forest, you sort of prefer late reionization, which means the reionization timeline goes a little bit more shallow, whereas the Lyman alpha emitters prefer earlier reionization. So by redshift 8, almost you're already starting the reionization, and then rapidly by redshift 6, your universe is fully ionized. So it happens quickly and it happens early. So this is basically, in order to explain this kind of reionization that Lyman alpha emitters are telling us about, you need a lot of bright galaxies to be responsible for reionization, which is kind of a puzzle because so far we have thought that reionization might have been mostly caused by low luminosity galaxies. So this has been further basically made into a puzzle puzzle when we look at Lyman alpha emit refraction at lower redshifts, which has been done by my student Spencer Fuller. And you can see that faint galaxies, which are here on the top, are coming out with the larger fractions compared to bright galaxies, which means more Lyman alpha escapes from faint galaxies than it does from bright galaxies. So they are collectively emitting more Lyman alpha in emission compared to their brighter counterparts. So here comes another puzzle: is who was really responsible for ionization? Was it the lower luminosity galaxies or the high luminosity galaxies? Mind you, both of these fainter and brighter samples are relatively faint. They're sub L star, but the trend is sort of continued in the literature where brighter than L star galaxies have also been studied. In addition, lower luminosity galaxies might have a lower offset of Lyman alpha with respect to systemic velocity. So this is plotted here in those symbols. And so these low luminosity galaxies that you see here have lower offset of Lyman alpha, which also in turn likely means that the Lyman alpha has easier time to escape. And so all of this together is a little bit of a puzzle, is into how do different, basically different classes of galaxies now really contribute to reionization. From some observations, we seem to be concluding that it's bright galaxies. From some observations, we seem to be concluding that it's faint galaxies. And so this is basically a puzzle. The other puzzle is as well, why do they even have such different properties to start with, and where does this come from? So the bright versus faint LEEs is a puzzle, and the question is why are their properties so different? And some of the answers to these might be simply into CGM around them being different, or maybe their physical properties are different. Maybe they have a different dust content in themselves. So here we go, another puzzle that we'll need to solve, hopefully with future telescopes. ALMA, of course, has been a driving force behind studying dust at high redshift. And with ALMA, we have been studying C2 in emission. And so here it's a plot of C2 versus star formation rate with some of the detections of C2. And if you look at bright galaxies, those detections seem to line pretty well with predictions from local relations from, say, Deleuze et al. But if you look at the fainter sources, which are here, once again, the same plot, C2 luminosity as a function of star formation rate, you can see that the lower luminosity galaxies, which are the two that are being circled, seem to be lying low on this relation. And so once again, there is a question why there is a difference at high redshift between low luminosity galaxies and high luminosity galaxies. In addition, there is also there is also low far infrared emission for low mass galaxies observed. And so the question is, what is this all telling us? Is the low C2 emission due to low metallicity, high ionization parameters? Are there strong radiation fields in there? Is there maybe no dust in those galaxies, in those low luminosity galaxies at high redshift? The problem with saying there is no dust is that we actually do detect dust in some of the galaxies, although not even nearly in all of them. So here are a couple of examples of 4 galaxies, and especially the top 3 are low luminosity lens galaxies. And they have surprisingly high dust masses for redshift 8. They have 10 to the 7 solar masses in dust in all these galaxies. And once again, we are back at the question, how do you create so much dust so early on? And what is this telling us about those galaxies? So let me conclude with saying, well, we still have puzzles of star formation. We don't really understand how stars are forming at redshift 7 in a very detail. And the 4 puzzles I have presented are whether the star formation indeed started earlier than we originally thought. We have a puzzle of timeline of reionization and who carries the load. Is it bright or the faint galaxies? We have a question of why C2 weaker in faint galaxies at redshift 6, and how do we produce those large dust masses in some of the redshift 8 galaxies? I'm guessing many answers will be enshrouded with dust, so dust will be answered to at least some of these questions, and I'm hoping Andrea will enlighten how they produce dust in their simulations. Thank you very much.
Thank you, Marusha. Thank you. Before going to Andrea, I have received a question from the audience. I think it's very relevant that you answer now. So in Max 1149, why does all stars have little spectral line emission while young stars have a lot?
Sorry, can you repeat this again?
Yes,
why?
I guess in the galaxy they were shown, the first one, the Max 1149. Why do all stars have little spectral line emission while young stars have a lot?
So young stars, we expect from young stars to have strong nebular emission lines. And what you're seeing in the Spitzer part of the spectrum is O3 emission lines. And so those nebular emission lines are a sign of young stellar population. And so that's a very common spectral feature of young stars. And then older stars would have less of those lines in the optical. And basically the way we constrain the relative amounts of the two populations is by measuring the presence of O3, which is, you also need high temperatures, of course, for excitation. And so that's why this is the case.
Okay, thank you, Marusha. I would like now to give the forum to Andrea. So Andrea, please start.
Yeah, thank you very much, Paula. You can hear me. I'd like to thank Paula, Giacomo, and Henry for setting up all this. Actually, always a pleasure for the opportunity to have science discussion again in these difficult times. So let me talk about the dusty normal galaxies in the epoch of reionization. So we have already heard from Marusha a number of issues from the observational side, and I think that and we can also determine their properties in terms of UV luminosity function, stellar mass density evolution, star formation rate evolution, size evolution. And a review with all these plots that I don't have time to discuss. I refer you to a recent review that we have written with Pratika Dayal. But in spite of this, we know very little about their interstellar medium, so the internal properties and the internal structure of these galaxies. So as you all know, the interstellar medium is a very complex system with a lot of microphysics going on. Multi-phase system with H2 region, molecular cloud, neutralized. Concentrate on one of these aspects, which is dust. And
Andrea, sorry to interrupt you. This is Giacomo speaking. Can you hear me?
Redshift is essentially dominated or largely dominated by the tend to form solid particles that we call grains or dust grains. So the idea that the high redshift dust population is dominated by supernovae comes from arguments in a paper that we wrote with former student of mine, Paolo Todini, in 2001. It's amazing, it's already 20 years ago. But so the first point we made there was that the evolutionary timescale of the typical producers of dust at low redshift in our galaxy, say, are evolved stars. But their evolution, the time that it takes to get to the stage at which they could produce dust exceeds the age of the universe if you are at redshift above 6 or 7. So you need to find some other source of dust. And the second point is that if the dust yield from these evolved stars is about 10 times smaller than the yield from core collapse supernovae. So clearly supernovae play a very important role in dust production at high redshift. And so we believe that we made this hypothesis or this suggestion that dust early on comes predominantly from supernovae. So this statement has been debated many times in the literature, and I think that the most comprehensive review or answer to this question comes from a recent paper by Lesniewska and Michalovsky, who computed, essentially, would put together all the dusty galaxies known at redshift between 6 and 8.3. And so the little points that you see in the two plots, the top one is for supernovae, and the second one is another source. But as you see, the blue line, that is what you get from supernovae, is sufficient to explain the dust amount that is estimated in all these early galaxies. On the contrary, if you look at the bottom plot, or the bottom panel better, then you see that these galaxies have dust masses that are not compatible with the production rate from AGB stars. So essentially, early dust comes from supernovae, and now is a more quantitative and statement that is based on galaxies that we indeed observe. So if supernovae work and AGB stars are facing a serious challenge in reproducing the dust masses that we see, then what are the implications? Well, the implications are that in addition to the dust production, there is also the idea that dust can grow into the ISM, into the interstellar medium, by putting together, collecting atoms from the gas, essentially. So if you have the source, the supernova seeding the dust grains, then they can grow in the gas. But this early dust grow is problematic. Why is that? There are three reasons. And these are detailed in a paper that I wrote a few years ago. So the first point is that early growth is problematic because of the high UV radiation fields that you have in these early galaxies. The grains gets positively charged. And therefore, it's easy to understand that if you want to stick a typically positively charged particle like the silicon plus or the carbon plus atom to a positively charged grain, this is very difficult. So it's very hard to grow because of the charging issue. The second point is that we have to keep in mind when we talk about high redshift that the CMB plays a very important role. Keep in mind that the temperature of the CMB at redshift 9 is already 27 K. And so the grains are also cannot be cooler than that. And so because of this hotter temperature as a floor, the stick to thermal motion. In molecular clouds, then they can grow. Yes, they can grow because the densities are higher, but they mostly grow icing mantles. That means essentially water and volatile species that, as soon as the molecular cloud is dissipated or or disrupted by the stellar activity, these grains go back into the ISM and these mantles are evaporated, so no grow again. So there are a number of problems that, that make dust growth very difficult at high redshift. So anything that you measure in terms of dust mass at high redshift has mostly or largely have to come from direct supernova production. So this is my first point. And so if the dust is predominantly due to supernovae, then the extinction curve that these grains, that the grain size distribution produced by supernovae produces is likely different from, for example, from the small Magellanic Cloud. And observations in quasars by Maiolino, Strata, and other people. I'm showing here an example of a redshift 6.2 quasar, and this is the extinction curve, and the solid line is the supernova dust extinction curve that we predicted in 2001, and it fits perfectly the data, which is the shaded curve. So observation seems to confirm that supernovae are the major dust producers at high redshift. Now, this analysis has been repeated a few years later in a larger sample of quasar, same result. In a sample of high redshift quasars, and again, it deviates from S. But according to our estimates, this is what it is, and it is consistent with the data. Now, as ALMA has went online, and in the last 3 or 4 years, essentially, we have discovered many sources which have astonishingly large dust mass estimates. So we have 4 examples here, there are more, and these are detected through the infrared emission, this time not in absorption. Important and need to be answered. So what produced this dust? Is the mass consistent with what we expect? What is the dust temperature? Can we predict the emission reliably, and so on and so forth? These are the type of questions that we would like to see addressed. And so with AMR, zoom simulations, then allow us to go to very high spatial resolution in a single galaxy, that is to zoom onto a galaxy. And this is one example. So this is our from a paper that we published earlier this year. And so you see that if you zoom in towards the center, this is on the picture on the right is 1 kiloparsec. On a scale, you see the bar there. So you see that in spite of the fact that the environment is very bursty with a lot of merging events, and there is a small disk of the size of half a kiloparsec or so. This is mostly molecular. These are where stars form. Is that because of the star formation is high, the UV radiation field, the interstellar radiation field in a galaxy is also very strong, and that has implication for what I'm saying later. Also important, relatively high metallicities are typically of the order of half solar. 0.2, 0.5, 0.8, so they're not 10 to the minus 3. So these are not, even if they are at high redshift, this is redshift 6. But we have also examples of higher redshifts, I'll show you in a second. The metallicity is relatively high. So these are evolved systems in spite of the fact that they live 13 giga-years away. So now we want to compare this simulation with specific data. And so we were very interested in this ALMA detection in band 7 made by Laporte on YD4, a lens galaxy in the Hubble Frontier Field. And so these are the ALMA images. This galaxy has a dust continuum, so it's been detected. The redshift is 8.38, and the estimated star formation rate is 20 solar masses per year. So this is the SCD that the authors published. So very nice SCD, very well constrained. So we try to reproduce exactly this galaxy and try to see what we could predict in terms of the SCD that should have been observed. So these are the results of the simulation. And so on the left, you see the UV map of the galaxy. So you see there's a lot of scattered light due to dust scattering in the UV. But on the right, you see the total infrared emission in the band between 8 and 1000 microns. And surprisingly, I found it of this galaxy comes from a few, maybe a 10 infrared bright UV optically thick with tau V larger than 8 star-forming molecular complexes. So this, indeed, these are essentially molecular clouds with stars embedded that are shining their light. The light gets absorbed by the dust almost completely, and the knots are shine up very powerfully in the infrared. And so we compute the SCD from the simulated galaxies, and we compare it with the observed point. So this blue point here in band 7 with HST. So because the nice thing about simulation is that we can also change the extinction curve at our will. So we experimented with the Milky Way, which is the black one, and the SMC. Of course, you see there are pH features in the Milky Way which are absent in the small Magellanic Cloud. The UV part, but they both fit well the infrared ALMA data point. So in this case, we find that the star formation rate, the actual star formation rate in the simulation is 78 solar masses per year, which is about 4 times higher than what was deduced from So this is exactly what I was just saying. So to the simulation, what is the dust temperature in the simulation in order to fit the SCD of this galaxy? Well, this is the answer. Just you can do the mean or the distribution in 2 different ways, weighting on the mass or weighting on the luminosity. Of course, what we observe is always the luminosity weighted temperature. And so pay attention mostly to the purple. This is not a single temperature. This is very important. Actually, there is a spread, and the mean is 91 K plus or minus 23. So the dust we predict that the dust in this galaxy YD4 has to be relatively, well, actually has to be hot. Of course, this is, keep in mind that here there is a mean on a distribution again. So there's not a single temperature, but is a multi-temperature gray body that we should fit in order to properly match the SCD that we were discussing before. Now, why, if this is true, if you believe what I just said, so you can ask me, why was dust hotter in the past? This is something that I'm going to discuss towards now the end of my presentation, but this is a clear trend. I'm showing this graph from a paper by Schreiber et al. And that shows the evolution of dust temperature in galaxies that are essentially in the redshift range between 0 to 4. And you see that there is a clear trend that the author also fitted with a simple linear law that you see in purple there. So as you go back in time or to higher redshift, the dust becomes hotter. And this is true no matter how you bin the stellar masses, the galaxies in terms of their stellar mass, which is what is shown in the upper panel. But the mean is clearly increasing. And if you pretend for a second that you can widely extrapolate this to redshift 8, then you will get a redshift 8 temperature according to this fit, temperature of order of 60K. So the dust is clearly becoming hot. So, but you say, why dust has to be hotter at high redshift? Well, we think, and we have just published, Laura Somovigo, my PhD student here in Pisa, has published a paper in which she shows that essentially this is an effect of the different condition of the ISM that are prevailing in high redshift galaxies. Here is this is a figure showing the temperature within a molecular cloud, within one of the knots that I showed you before, that is emitting the infrared radiation. So because in the high redshift galaxies, the pressure of the ISM is higher, the molecular clouds are much more compressed, and so the dust is much closer to the source. And so the temperature goes up. So this is simply a very simple argument. And you see that in the typical high Z molecular cloud, which is the cyan line, noted by high pressure, then the temperature can become, there's a gradient, of course, at the center of the cloud, the temperature can go up to 100K, and then smoothly depth, both in the UV and the infrared, but are not relevant. So clouds are hot. Then clearly the dust masses that we are computing may change a lot. And in fact, because we know that the total luminosity is proportional to the product of the dust mass times the temperature to power 6, essentially. So as you change the dust temperature, you also change the dust mass. And so for fitting max 0416 Y1 at redshift 8.3, Asano et al. Show that there is a tension if in the dust mass that they expect as a function of the age of the stellar population that can only be, that represents a problem, because if you say that the temperature is 40K, then you would require that each supernova produce 4 to 8 solar masses of dust. This is, nobody could dust temperature. The infrared luminosity of the galaxy with a beta slope in the UV. It has been noted that many high redshift galaxies, particularly those in the Kappa sample that are the pink points, lie below the expectations from local relation based on the Calzetti-Meurer law. But that was a problem. So why are these galaxies, the pink points here, why are they under luminous in infrared? Well, this is because their luminosity that's being computed here by the refraction in the temperature, then you move all these points up, and everything again at least is more reasonable. We have better measurements. So let me conclude. And so there are aspects of the structure of high redshift galaxies that have very important implications, particularly for the dust that we're interested here today. So they are compact, they are already dust and metal enriched, even because that enrichment proceeds very rapidly. They have a large star formation rate per unit area, and the strong interstellar radiation field. All these aspects go source is produced rapidly and early by supernovae, we think, with little dust growth thereafter. The dust tends to be hotter because it's formed close many estimates we are doing for these high redshift galaxies, in particular the dust mass and the IRX beta relation. It's interesting to note that most information obscured and escaped UV determinations. So just the final thing, so what do we do from now? I think that for the future, SPEAK and JWST will help us constraining the dust temperature and the pHs, which is also another important point. The presence of pHs in these early galaxies, we can determine the dust content because we will be able to also to explore the VM part of the gray body spectrum, and there will be a key synergy with JWST in terms of studying also the stellar population of the first stars. Thank you very much.
Thank you, Andrea. Unfortunately, there has been some problems of connection, so sometimes your voice has disappeared and your slides were slowly appearing. So maybe we can try to fill the holes with questions. I would like her to invite the two of you to ask her to start a dialogue between you and start asking questions. Maruja, do you have questions to Andrea?
Well, basically, the high-level questions I already put in as puzzles is, you know, so you think that forming such a large amount of dust in those high redshift galaxies is not an issue?
Well, as I was trying to say, I don't think, first of all, I need to be convinced that the dust masses that we estimate are correct. In the sense that it could be that if dust is hotter, then you need much less dust than what we think. Okay, because keep in mind that this is an open question. We don't have an answer to that. In terms of in terms of mass, there could be a problem because, of course, given the stellar mass that you observe, if you can estimate that, then you have an upper limit on the amount of dust that you can form, assuming reasonable, I think, yields that we can at least test locally. So we know how much dust we must have as a maximum. Okay, and so this. You convinced us that stars start to form early on, maybe already 15 or 16, or I see that the connection is a little bit flickering. Sorry about that. I was saying that the star.
Yeah. Maybe you can stop sharing the slides so we may have saving.
Yes, absolutely. I was saying that producing this dust early on I don't think it's a problem, because if supernova do that, then basically it only takes a few million years in order to get to that stage, and so you can produce dust early.
But then you also need stars to start forming early.
Absolutely, yes. No, I totally agree that well, in your galaxy, for example, in MAX 1146, you do see, do you have an estimate of the stellar mass?
Yeah, I'm not sure from the top of my head. I believe it's 10 to the 8 solar masses, if I'm not mistaken. It's quite a large amount of mass, which is then hard to predict in such a short amount of time, which is why there is the tension.
Okay, so yeah, so see, you can form because you have yields of dust, right? So Yeah.
So Andrea, do you have questions to Marusha?
Yeah, I was going to ask you, so how robust is the age determination of 290 million years for your galaxy? So how good is the fit, or how confident are you that this is a good number?
I mean, this is not my fit, so I cannot really tell from the first hand. But what is an issue here is that you do need to form 4,000 angstrom break, and in order to do that, you need to form large amount of A stars, and this is the 10 to the 8 solar masses in stars is hard to form. On the other hand, you cannot get away with forming all these stars in a young stellar population, because then you would also expect stronger O3, which we don't observe. We have an observation of how strong O3 is in this galaxy from ALMA. So that's why I'm pretty confident in this 290. I mean, there is a plus or minus probably 50 to 100 error bar on it, but you need to go beyond A star lifetime, and so you're getting into a couple 100 million years old stellar population for sure.
Okay, and the fact that there are observations that suggest that reionization could be due to high mass galaxies, rather than faint low mass galaxies. So what makes you think about that?
So I think we are seeing a pretty rapid reionization timeline, and it's hard to explain this with low luminosity galaxies being the dominant. So I'm not entirely sure what is happening. So either we'll find some strong evolution of Lyman alpha properties between redshift 6 and 7 and 8. Because this test that we are making with Lyman alpha emitters assumes that nothing changes between redshift 6 and 8. Not much changes in the general population. And so I'm guessing we are going to not just learn about the reionization timeline, but we are also going to learn about galaxy properties evolving quite rapidly at those redshifts in a way we don't understand right now.
Yeah, and well, finally, that I stop. But so you also mentioned the fact that there could be plenty. Well, we know that there could be plenty of cold dust because at high redshift the CMB temperature is relatively high. So if you have a lot of dust, let's say at 25 or 27 or 30K temperature of the CMB, you can easily hide that and just see it in absorption. What do you think about that?
Yeah, I'm not an expert on this at all, and I'm not sure what this is. I mean, you are telling us that dust has to be hot, so I'm not sure how you could reconcile this together.
No,
I'm throwing this out as a wild speculation, not actually saying that this is the case.
No, I mean, this is what we are getting from our simulations. On the other hand, that will be good, because if the dust is hot, you don't have to worry too much about dust that you can't see in the CMB, because it's much hotter. So that is good news. So we are not missing so much dust.
Yeah.
Well, I have a question for both of you about the role of population 3 stars. First, the observational evidence of population 3 stars. Marusha, do you have anything in your high redshift spectra hinting at their presence?
We haven't seen anything that I would call convincing evidence of POP3 stars. The problem is those spectral lines that they would likely produce, they're very, very weak. And so our spectrographs are not up to task to really see those population 3 stars. Also, sometimes it's hard to figure out whether it's AGN contribution or POP3. So I think we do not have observations yet. There's some hope that we'll be able to see those more readily with JWST, and especially if you have lensing objects, because you need crazy big magnifications to really detect those POP3 stars. So hopefully, but I don't think we see any strong evidence yet. That doesn't mean they don't exist. I just think our observational instruments are not up to task yet to do so.
Yeah, for me, I would say that they are interesting, and actually they're very good dust producers according to calculations. But clearly they are very rare objects, so they're interesting but very rare. So I'm not sure what is their impact on the full evolution of galaxies. Of course, discovering them would be great, but I don't think they have a major impact on the structure of galaxies. Maybe on reionization, though. On reionization, they could be at least start reionization, that's for sure.
And in the production of dust?
Well, of course, this is a very wild speculation because we know so little. But in principle, because they are massive stars, they should produce a lot of dust. That's true. Yeah, at least according to some results.
So I have a questions from the audience. From theoretical works, we have a PDF of dust temperature, which is not completely made of hot dust. Correct me if I'm wrong.
Sorry, I think I've had a glitch. So can you repeat the question, please?
Yes, sure. So from theoretical works, we have a PDF of dust temperature, which is not completely made of hot dust. Correct me if I'm wrong.
Wi-Fi, switch to another one, see if it works better.
So you missed the question completely.
Yeah, sorry, there's a, let me, well, now it's okay, but there's some problem today here. So you want to try again, or you want me to change my Wi-Fi?
Shall I repeat the question?
Very quickly.
So the probability distribution function of the dust temperature is not completely made of hot dust. The question is, these are from theoretical works. Is that true?
Okay.
I'm trying to change my network. Just go ahead with the question for Maruza.
I can give some comments on that.
Yeah.
I mean, I'm not a theoretician, but I see the question had a follow-up. How do we reconcile hot gas and the one at the CMB temperature? So I wasn't saying that there isn't cold dust. It's just if you because the CMB temperature is hot at this early times, you would potentially see you wouldn't see it in ALMA observation necessarily. It would need to be shielded somehow. So, but I'm going to leave this to Andrea because this is more a theoretical question.
No, it seems to be in better shape. So Paula, fine, apologies again. So repeat, and now it seems to work okay.
I guess the question was to Marusha. She was asking how we reconcile the hot dust and the one of the CMB temperature, but you have answered that. So, yeah.
Yeah, okay. So do you want me still to answer, or do you want to?
Please go ahead. Sure.
I think that the CMB just gives a floor in the temperature. So anything that is in thermal equilibrium cannot be colder than that. But of course, there are other sources like stars, obviously. So because the dust temperature is high, if you believe our results, then it should be okay.
We lost you in between a little bit, Andrea.
I don't know what to do. So yeah, I was saying that essentially if the dust is hot, there is no problem with the CMB because there's little hidden dust because the dust is a temperature higher than CMB, therefore is not affected in terms of visibility.
Okay, there is another question so related to the emitting regions, because it looks like this is both a question from a theory point of view and also observation point of view, where we have evidence that the far infrared emission and the UV emission do not come from the same regions. So you have a patchy distribution, so you may not have a complete picture while you're observing either with HST or observing with ALMA. So you have something which does not match.
Yeah, I agree. This is absolutely what we see in our simulations. So you see that the infrared and the UV are very much spatially separated, segregated. And so most of the infrared comes from the giant molecular complexes that have embedded stars, while the UV is mostly coming from stars that have get rid of their molecular environment, and now they're shining in the UV. So the spatial segregation is an issue.
So I have another question from the audience. Carniani, Ferrara et al. 2020 show that the C+ in Z above 6 galaxies, very diffuse and only recovered by tapering the data. How is this consistent with the idea that the dust is hot being in a compact ISM?
Well, in that paper, we were showing that indeed the carbon-2 distribution is found to be relatively extended, certainly more extended than the UV. Keep in mind that I was saying before that the dust is located close to stars and gets hot. It's in giant molecular complexes. Then there is also diffuse carbon in the diffuse ISM that shines, but the emission of dust embedded in that gas is negligible compared to the one that comes from the molecular clouds.
And so there is a C+ emission and not dust. So and
there is
what is the energy sources pumping up the atomic?
No, sure, it's UV for both, but I'm not saying that there is no dust or dust is not emitting there. It's just the signal from dust in the extended halo is too faint. So you see the carbon-2, but you don't see the dust because the signal is too faint.
Yeah, so there has other questions from the audience. In the near universe, we see large amounts of dust associated with luminous blue variable stars. This dusty nebula can be very extended and possibly not reach from the subsequent supernova shock, so the dust yield may double that of core collapse supernovae.
That's certainly possible. I don't know if it is a question for me, but I'll try to give it.
Yes, well, I have written to whom.
So it's certainly possible. Now, clearly, in the galaxy, there is pre-existing dust, and also there's been time for normal stars or evolved stars to get to the stage at which they can produce dust. But at early redshift, all this cannot be possible because you start from zero metallicity and you have to start from scratch with supernovae, which are the first dust producer, and they start to produce dust. Then dust accumulates. But at redshift 0, of course, there are many other sources that contribute to the dust formation.
So there are not similar studies in galaxies at high redshift, but in lower metallicity, large Magellanic Cloud, we see significant dust masses, I guess from supernovae. Any comment about that?
Yes, I mean, sure, there is dust. I'm not sure what the question here. So sure, there is dust in even in low mass galaxies that are redshift, in particular in the Magellanic Clouds. But I don't. Sorry, maybe I don't understand.
I think they okay. I'm sorry because the question is split in several sentences. It's not clear. Typical dust temperature around LBVs. So I guess this is a luminous blue variable stars, is about 70-100 Kelvin.
Yes, that's okay. I mean, if you're close, as I was trying to say, in this cloud that Laura Somovigo is simulating, we do see that the dust close to the center in these molecular complexes can get exactly to this temperature, to up to 100 K easily. I agree.
Okay.
I think the high redshift temperature that you were referring is more of an average temperature of dust that you use. So I think that's where people get confused by saying, you know, at low redshift the temperature is low, but you know, on average, not around stars and such.
Sure, it's essentially the luminosity weighted over the galaxy. This is very important. It's also very important to keep in mind that dust is not a single temperature. So when we fit a single temperature gray body to the SED, clearly this is a very rough approximation, but it gives us an idea.
Okay, I don't see any other questions from the audience. Or do you have any other questions or to each other?
Marusa?
No, I mean, I think we're pretty clueless is the answer of what dust is really doing. I think the observations are clearly lacking, I would say, or, you know, awaiting higher samples of data, which is of course difficult because these are galaxies at redshift 9 are really difficult to observe even with HSD, and then following them up with ALMA has been challenging. And so I think it's up to us to generate more data to really see what is going on, and hopefully we'll be able to give some more answers to what the dust is doing really at high redshift.
Yeah, but I would say that we have done so many progress in the last just 5 years, detecting all these sources. So that's amazing for me.
That is true. ALMA has done an amazing job and also Spitzer in detecting these sources. So we have puzzles now, which is much better than what we had. If I gave this talk 5 years ago, I don't think I'll be able to talk much about anything. We'll just be, we do have high redshift galaxies. I think we would have shifted high redshift to redshift about 5, not 9. We would be involving ionization at that point.
Yeah, I agree. So I think it's, well, it's an interesting area. It's very much in development. And I think that the synergy also with JWST will allow us to learn a lot, and possibly in the future, even with Speaker or other infrared instruments.
Yeah. So there is another question, how do we go from the average dust properties, so single photometric data points, to a more complex and realistic picture of the structures of dust in high redshift galaxies?
Well, as I think it's key to sample the SED in a better way. So already with ALMA, we could hope to go, for example, to band 9, and so getting closer to the thermal peak. And of course, Spica or JWST, Spica would be fantastic, right? Because it would just sample the VM part of the gray body. That is what we need in order to accurately determine the effects of the multi-temperature distribution and determine the mass very solidly, and so on and so forth. So, but with ALMA, we're already making progress, and there could be other tricks that we can use in order to connecting this with other indicators like the carbon-2. So maybe there are ways that we can explore in which we can get better and more solid numbers.
The other thing I think that one could add is, of course, spatially resolved observation. So you can actually study the properties, as in how they're distributed spatially within galaxies, and how does this compare with UV light and optical light and so on. And that can definitely help figuring out where does dust live and how it's distributed.
And how much we are mistaken if we assume that the dust formed by early stars has a similar properties as the dust in the Milky Way?
This is a beautiful question. I mean, we don't know. Actually, this is something that I keep thinking a lot. But already at this stage, just taking the galaxies that we have at our redshift, which are maybe a tenth on which we can do the type of work that I show for YD4. And already from YD4, clearly you can see that the Milky Way does pretty well. It's not that far from what we observe locally in fitting the SED, of course. But the SED is very poorly constrained, on the other hand. So we don't know. On the other hand, we do expect also that dust produced in supernovae has a slightly different composition. So these are all things that, at the moment, truly speaking, we don't know. At least I don't know.
Okay, I think I don't see any other questions, so maybe we can thank you again and stop here this dialogue. I hope that to be able to see you in person, not too far in the future. So
Yes, please.
Thank you again, and sorry for this interruption of technical problems. This happens.
Probably.
And I give back. I don't know whether Giacomo or Henri, they want to say anything or to conclude, or we can.
Yeah,
stop.
I can just, Paola, sorry, just to, let me also, from my side, on behalf of also from Henri, so let me thank very, very much Andrea and Marusha and you, Paola, for giving life to this very beautiful event. Thank you very much. It was exactly in the spirit of a dialogue, a duologue with some slightly controversy. This is okay. It was very nice. Thank you very much. And let me just remind to our to everyone that there will be only one more event on the 20th of July. And please check on our web pages, and we will. And anyhow, as I said at the beginning, we will collect all the questions and give to Andrea and Marusha, and then we will publish very soon on our pages all the answer in a PDF form. So I'm saying that, thank you very much again. Thank you. And see you, hopefully, exactly. See you soon live very soon. Bye.
All right.
Bye. Thank you.
Ciao.
Ciao.